All right, now everybody, we are moving on to section 5.3 today, where we relate definite integrals and antiderivatives. That's our ultimate goal, but before we get there, we have to have some properties that we have to address. So here is what your do now would have been had we actually had in-person school. You can pause it, try these out. I mean, it's really just practicing your derivative rules. Here's all the answers. You can pause and look at those real quick. But moving forward, that would have been a homework quiz. And now here we have all of the properties of definite integrals. They all have really dumb names. And by dumb names, I mean they're just like obvious names. Like the first one, order of integration. Order of integration is referring to what happens when we flip-flop the limits of our definite integral. And if we flip-flop the limits of the integral, what I'm saying there is instead of having the integral from b to a of f of x dx, we take the integral from a to b of f of x dx. They're opposites of each other. So the integral from b to a of f of x dx is equal to the opposite of the integral from a to b of f of x dx. If you flip the limits on an integral, change the sign. Next one we have is the zero rule for definite integrals. So the zero rule just talks about taking the integral from a number to itself. If we're talking about that, we have zero width to the area. So we have zero area there. The integral from any number to itself of f of x dx is equal to 0. So the integral from a to a of f of x dx is equal to 0. Again, that is a definition. Constant multiple. Since a definite integral is itself a limit, we can move constant multiples outside of an integral. So if we have the integral from a to b of k f of x dx, where k is some arbitrary constant, we can just shift that k out in front of the integral if it makes our calculations easier. And we kind of played with that last section. What that means is if we have the integral of an opposite function, that is the opposite of the integral of the function. That's just pulling a negative out of there. All right? Sum and difference rules. If it is easier to split up a sum of two functions and calculate the integrals themselves, well, that's what you do. Sum and difference rule says the integral from a to b of f of x plus or minus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And please note all the limits have to match up there. Yeah. Next thing we look at is the sum and difference. I don't know why I have that twice, but I do. Additivity is talking about when you combine two integrals that have the same integrand. So if the integrand is the same, then the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. And if you want to see why that occurs, keep in mind we're talking about area underneath of a curve. So let's just make some arbitrary curve. Let's call this f of x. If I want to find the integral from a to b, that's that green area right in there, right? Now if I want to find the integral from b to c, that's that purple area. Dang it. I wanted a highlighter with purple. There we go. That's that purple area right in there. The integral from a to c is just all of that colored area right in there. If you are adding two integrals together and the integrand is the same and the upper limit of the first matches the lower limit of the second, you can just cut out that middleman. You can just talk about the integral from a to c of that. Min max inequality refers to if max f and min f are the maximum and minimum values of f on a to b, then min f times b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to f times b minus a. I call this like a big duh because I can draw, again, an arbitrary function. Let's draw, this was explaining number 5, we're going to explain number 6 down here. If I have some sort of arbitrary function, let's just call it, looking like that, right? And I have from a to b, right? We are now talking about min f being the minimum of the function and max f being the maximum of the function on that closed interval. Keep in mind, since we're talking a closed interval, extreme value theorem applies. So let's draw in the minimum and the maximum. Min feels like a red to me. There's the minimum of that function. The maximum, that feels like a green to me. There's the maximum of that function. All this theorem is saying is the area underneath that curve is in between the maximum times the width of the interval. Basically, what it's saying is we have a maximum rectangle. We also have a minimum rectangle, where we have the min times b minus a. That area has to be somewhere in between the maximum rectangle and the minimum rectangle. And the last one that we have here, the domination. If f of x is greater than g of x on a closed interval, then the integral from a to b of f of x dx is going to be bigger than the integral from a to b of g of x. Domination just means when a function is bigger than another function. So if f of x is bigger than or equal to g of x, then the area under the curve of f of x is bigger than or equal to the area under the curve of g of x. And this relates to if f of x is purely positive, then the integral from a to b of f of x dx is purely positive. We actually did that last section. So there's your 7 rules that you need to know for integration. Let's try to apply those rules right over here. You can see we have some information up top. Integral from -2 to 3 of f of x dx is equal to 2. Integral from 3 to 5 of f of x dx is equal to -9. And integral from -2 to 3 of g of x dx is equal to 5. We can actually answer some of these. There are some that are impossible to answer. We'll try to explain exactly why some of those are impossible to do. Maybe give these a shot. You might be able to do them, pause it, and then come back. So I mean, looking at number A, I can see just with A in particular. Come on, give me a pen. There's a pen. With A in particular, I can see it looks almost identical to that first statement, except for the fact that the limits are switched around. So using that that first, not the first, but I think it was the second rule. Oh my gosh, I can't remember which one it was. The first rule, the order of integration. Order of integration, we can just flip-flop those limits, change this to the integral from -3 to 2, and make it opposite of f of x. So the integral from 3 to -2 of f of x dx is equal to the opposite of the integral from -2 to 3 of f of x dx. And we happen to know that the integral from -2 to 3 of f of x dx is 2. So this ends up being -2. Again, you only know that because of what's given to you. Looking at that second one, integral from -2 to 5 of f of x dx. Well, let's see. Look up here. I know the integral from -2 to 3 of f of x dx, and then the integral from 3 to 5. So it looks like I can go through 3 to get to 5. So using that additivity rule, again, additivity I think is on the second page. Yeah, right here, that additivity rule, I can just eliminate that middleman. So this is going to be equal to the integral from -2 to 3 of f of x dx plus the integral from 3 to 5 of f of x dx. And looking up here, just putting in values, I've got this is 2 plus this is -9. 2 plus -9 gives me -7. Looking at the letter C might look slightly difficult, except we recognize we've got a difference in here, so we can split that up into two different integrals, and we've got arbitrary constants in here, constant multiples. We can change this to the 5 times the integral from -2 to 3 of f of x dx minus 2 times the integral from -2 to 3 of g of x dx. And looking back up, hopefully we have this information. If we do, we can finish it. 5 times integral from -2 to 3. Hey, right up here, 2. 5 times 2 minus 2 times integral from -2 to 3. 5. So that ends up being 0, just from the stuff that we're told about. Now we get into some like really weird ones. None of these are possible. I will tell you why some people think that they are possible, but they are not possible. I do see a lot of times on part D, we have 4 to 5, integral from 4 to 5 of f of x dx. Some people look up here and see we've got the integral from 3 to 5 of f of x dx. So I've seen people in the past take half of this for the answer for D. But the answer is, it is not half of -9, because we don't know what happens between 3 and 4 over here. So we can't make any assumptions. We can only determine stuff off of what we know in this situation. So this one is a legitimate IDK. I've seen that on tests before. You might want to clear it up like, I don't know, because I'm not told what happens between 3 and 4 of f of x. Now looking at integral from -6, let me start that over again. Part E, integral from -4 to 6 of g of x dx. I've seen people in the past see that -4 is twice -2. They see 6 is twice 3, so they think that this answer is twice 5. But no, we can't make up stuff about our limits. We don't know what happens between -4 and -2 up here, or what happens between 3 and 6. So this one is another, you got me. And of course, we would want to explain that a little bit further. We don't know what happens between -4 and -2, or between 3 and 6 on g of x. Now over here, we can see that this is a sum, so we can split it up to the integral from -2 to 5 of f of x dx plus integral from -2 to 5 of g of x dx. And we happen to know this, we already did it. This one right here is -7. Plus, but we don't know this one over here. The integral from -2 to 5, I only know what g of x does between -2 and 3. So this one is a big old question mark. No clue. So the top 3 are possible, the bottom 3 are not possible, mostly because we can't make up stuff about our limits. That's pretty much the big sticking point on these. All right, let's go forward. There's the answers. You can see them behind me. So now we need to talk about what an average is. And an average is where you add up all of the numbers in a particular set and divide by the number of numbers. We actually have a different way of calculating an average in this particular case when we're talking about our definite integrals. So when I'm looking about totaling up all of my numbers, really in that case, if I'm talking about adding up all the numbers underneath of a curve, let's just set up an arbitrary curve from A to B. If I'm trying to look at all those numbers of the function are the heights of that function. So I'm trying to add this number, and this number, and this number, and this number, and this number. You guys see what I'm doing here? Hold on, let me get really fast at filling. So now I've drawn all of those numbers in there. What we actually have here, instead of the average from what we've done before, where we have the sum of all of the numbers divided by how many numbers we have. When we sum our numbers here, we're actually just finding the area. So our average in this case is going to be the integral from a to b of our function, and we need to divide by the numbers that we have, and that's just going to be the length of the interval. So in this case, that's how we're going to find our average. 1 over b minus a times the integral from a to b of f of x dx. So basically what you're looking at here is it's taking that area and flattening it out to some value that we would call the average. So if f is integrable on a to b, its average mean value on a to b is the average of f is equal to the 1 over b minus a times the integral from a to b of f of x dx. That is an important thing that comes up every year on the AP test. This is the average value formula for a function. If I ever say what is the average value of a function, this is the formula that you need to have memorized. 1 over b minus a times the integral from a to b of f of x dx. Write it down, write it on one of your note cards that you study from. You know it now. It's indelible in your brain. Which allows us to do this problem. Find the average value of f of x equals 2 minus x squared on the interval from 0 to 4. Does f actually take on this value at some point in the given interval? One of the things in the average value there was if f is integrable. I'm just going to tell you right now that f is integrable right here. As long as you don't have any infinite discontinuities, it's going to be integrable. So here, in order to find the average, I'm just going to fill out the formula that I have back here. Remember, average of f is 1 over b minus a, integral from a to b of f of x dx. So here, I know that my average of my function is going to be equal to 1 over b minus a times the integral from a to b of f of x dx. And then you calculate that any way you know how. Are you guys ready for the hint that is back here? There's your hint. Your hint is to use nint to find the integral from 0 to 4 of 2 minus x squared. If you don't remember what nint is, remember we went through last class how to use our magic graphing calculator machine to find out those definite integrals. We're allowed to do that now. So looking here, I know that I'm going to be finding 1 over 4 minus 0. Honestly, if I'm doing this myself, I would just call that 1/4, maybe even put it in as 0.25. Some way, shape, or form, I get fn int on there. 0 to 4 of 2 minus x squared. I don't know what that 1 is about there. Okay. dx. Hit enter. Oh, look at that. It's negative 3.33333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333. So again, I see that this is, give me a pen, is equal to negative 10 thirds. All right, cool. So I found the average value on my interval. Now I look to see the second part of the question is, does f actually take on this value at some point on the given interval? To figure that out, what I have to do is take this value and plug it in for the function. So I'm looking to see, does the function 2 minus x squared equal negative 10 thirds at any point on the interval from 0 to 4? Now looking at that, I could, let's see, subtract 2 from both sides. I would subtract 6 thirds. I would have negative x squared is equal to negative 16 thirds. divide by -1, I get x squared is equal to 16 thirds. Square root both sides. I know that I'm going to get x is equal to plus or minus the square root of 16 thirds. I mean, really, I could call that 4 over root 3 or 4 root 3 over 3. Any of those works. Any way you look at it, really, I'm trying to find out, are either of those values on the interval from 0 to 4? And indeed, yeah, it is. I believe the positive one is between 0 and 4. Just to double check, I can whip out my calculator here real quick and just see what is the square root of 16 thirds. 2.309. Yeah, that's definitely between 0 and 4. But is that just like coincidence, or does that happen every single time? Well, let's take a look. By the way, here you can see 4 root 3 over 3 is on the interval from 0 to 4. And again, we're asking, does that happen every single time? And yeah, it does. Because what we have is the, we're going to draw an arbitrary curve, right? So arbitrary curve feels like we've done this before. We'll call that f of x. We've got the integral from a to b. If I draw my min and my max rectangle, min rectangle, max rectangle, what I see there is I have the area is in between there. So again, looking at that, I've got just the Min Max Theorem. We said min f times the b minus a is going to be less than or equal to the integral from a to b of f of x dx, less than or equal to max f times b minus a. Remember that from way earlier today? Let me just show it to you real quick. Number 6 right over here. Remember how it's just kind of like one of those duh? The biggest rectangle is definitely bigger than the actual area, and the smallest is definitely smaller than the area. Well, we just took this inequality and copied it over to here. When we copy it over to here, I can now go through and I can divide everything by b minus a. And now what I'm guaranteeing is the minimum of the function, the smallest value on the function, is going to be less than or equal to 1 over b minus a times the integral from a to b of f of x dx. And it is going to be less than or equal to the max of the function. As long as this function is continuous, I'm going to guarantee that at some point on this interval, I'm going to achieve the average value. That is so important that we make another theorem out of it. That theorem is called the mean value theorem for definite integrals. And if f is continuous on the interval from a to b, then at some point on the interval, f of c is equal to the average of the function. You might want to write that down, put it in your notes. That's going to be important. I know it'll come up again. Now we're going to move into the book. It's Exploration 2 on page 289. So open up to page 289 just so that you can follow along here. And this is the activity that we want to do. It looks very confusing, but note that the number 1 is just copy the graph onto your paper and choose any x greater than a in the interval a to b and mark it on the x-axis. So copy over the function, this right here, and mark an x on the x-axis. I'm going to do it up here in just a second. I actually have this on my screen right here. So I'm going to choose my x, but I want you to choose an x first. So here I'm going to put my x. I'm going to put my x right there. You could have your x being before that 0, you could have it being between the two zeros, or you could have it after the second 0. So that part that I pointed out, that your x could be in a different location, is going to change how number 2 works out. Because number 2, using only vertical line segments, shade in the region between the graph of f and the x-axis from A to B. All right, so shade it in. If you don't know what I'm talking about here, let me just show you here. Shading it in, I draw in with these vertical line segments. Remember, like I did a couple of slides ago? What we should recognize is those vertical line segments really represent really skinny rectangles. Let me shade it in real quick. So you can see now I've shaded that in entirely with vertical rectangles. Let's see what 3 is asking us. Okay, so your shaded region represents a definite integral. Explain why this integral can be written as the integral from a to x of f of t dt. Why don't we write it as the integral from a to x of f of x dx? So first off, that is the definition of a definite integral. Definite integral is just the area underneath the curve. So we've now, I mean, you should have been putting that together, that we were shading in a definite integral. What we really wanted to drive home in number 3 is why we should put it down as the integral from a to x of f of t dt. The really driving it home kind of component is, let me pull myself up here. So why do we use t in here instead of over here we called it f of x? And if you're not putting this together, it's because now we've called x the end of our interval. And because we were able to choose where our x is, our area here really depends on the placement of x. So our upper limit has to be that variable x. Since we already used it up here, we have to use some other dummy variable inside of the integrand and the differential just to make the math work here. So that is why we don't use integral from a to x of f of x dx. So I guess number 4 reflects what I just said here. Compare your pictures with others produced by your group. Notice how your integral, which is a real number, depends on which x you chose in the interval from a to b. The integral is therefore a function on a to b, and we're going to call it capital F. Now, going back over to here, oopsies. There we go. There we are. Depending on where you chose your x, if your x was before the first 0, you wouldn't have been taking away any of the values for these guys down here. Really, what we look at is the amount of area depends on where we choose x to be. All right, so now what we're looking at here is we're looking at this function is going to be equal to capital F of x. All right, we're just arbitrarily calling it capital F. Now when we look at the next, oops, sorry, I accidentally paused instead of turned on my doc cam. When we look at the next step, we're looking at number 5. So we should remember that f prime of x is the limit of delta f over delta x. Don't worry about that right now, but as delta x gets smaller and smaller, all right? So don't worry about that just yet. Represent delta f in your picture by drawing one more vertical shading segment to the right of the last one you drew in step 2. Delta F is the signed area of your vertical segment. So looking back over here, we're going to draw another vertical segment to the right of where we stopped. That vertical segment, I'm going to make slightly bigger. I'm going to make it into a giant rectangle. And that giant rectangle is going to be the change in my area. That change in my area, I'm just zooming in right here. That is equal to, let me make it a little bit clearer. The area of this new segment is equal to delta F. It's the amount of area that's being added onto this function. Let's look back over here. Represent delta x in your picture by moving x beneath your newly drawn segment. That small change is the thickness of your vertical segment. Okay, so let's go back over here. We know that delta x just means the change in x. So that's how much we've gone over to get that new segment. So looking at this big rectangle, I see that I've got delta x right here. Next thing I have to look at is step number 7. What's the height of your vertical segment? The height of our vertical segment, well, the height is just represented by the function, right? The function is just what f of x is. So down here, this rectangle is equal to f of x. Now let's look over here. The area of this rectangle is delta f, right? Because it's the amount of area added on here. But in addition, since this is a rectangle, I can say that this is equal to f of x times my delta x. Well, golly gee, looking at this, I can divide by delta x, and I have delta f over delta x is equal to, delta capital F is equal to f of x. What we're saying here is if I took the limit here, limit, again in step number 5 there, it says f prime is the limit of delta f over delta x. Let's look back over here. That makes f prime, also known as dx of f. Well, we defined f as the integral from a to x of f of x dx is equal to f of x. Wait a sec, wait, hold on, wait, no. Oopsies, I did a big oopsie here. We talked about this oopsie. The variable in the integrand can't match the upper limit. So this has to be f of t dt. That's a huge thing. What we're saying now is if you take the derivative of an integral, they cancel each other out. The big secret that I have for you guys right now is derivatives and integrals are inverse operations. Integration is indeed the opposite of differentiation. That's a huge thing. That's this right here. I'm trying to blow it up so you guys can see it better. I know when people are in class, they always complain about not being able to see the yellow boxes. So that is massively huge. But wait a second, even further. We talked last chapter that we had a word for, not last chapter, 2 chapters ago, I think. At some point we talked about undifferentiating stuff. When we undifferentiate, we call it an antiderivative. So now we know that the antiderivative and the integral are the exact same thing. So we know now that the integral, I need a pen. There's my pen. We now know that the integral from a to x of f of t dt is going to be equal to, using our notation from antiderivatives, we used capital letters. So we're going to call that capital F of x. And we remember from last chapter that we need to have a plus c. That's called the constant of integration. You now can understand why it's called the constant of integration. The integral is equal to the antiderivative plus some constant. We can actually solve for that constant if we just make up another, here, I'm just going to put some scratch work over on the right side of my paper. If I change my upper limit just to a, this becomes the integral from a to a of f of t dt is equal to capital F of, well, I changed my upper limit to be in here, capital F of a plus c. Well, that's cool. That seems about useless, unless I recognize I've got an integral from a number to itself, so I know that this is 0. Okay, this is going to be helpful. All right. I can now solve this for c. I now get negative f of a is equal to c. So going back over to the left-hand side of my paper, I can now find out how to calculate an integral by hand. So the integral from a to x of f of t dt is equal to the antiderivative at the upper limit minus the antiderivative at the lower limit. That's hugely, massively important. We can now calculate our definite integrals as long as we know what the antiderivative of a given integrand is. So like, let me teach you guys how to keep track of all that notation. Like, let's look at that to find out what the integral from 0 to pi of sine of x dx is. By the way, I know that this is 2. How do I know that's 2? Because I paid attention last class. That was given to us in one of the activities. In order to calculate what the integral from 0 to pi of sine of x dx is, I like to do this in a couple of steps. The first step is finding the antiderivative of the integrand. So I look at sine and I try to find out what function gives me a derivative of sine. Well, I know the derivative of cosine is negative sine, so the antiderivative of positive sine is going to have to be negative cosine. When I do this, I put it in a boxy bracket looking thing. And that's just saying I've calculated the antiderivative. Outside of the boxy bracket looking thing, I put my lower limit and my upper limit right outside there. So now when I'm evaluating this, I separate it into 2 different steps. Step 1, find the antiderivative. Step 2, evaluate. So now evaluating, I've got negative cosine, and going off of what we had on that previous page, negative cosine of the upper minus negative cosine of the lower. And now when I look at this, I can find, let's see, just using my unit circle here. I've got pi, and I've got 0. At pi, I've got negative 1, 0. At 0, I've got 1, 0. So looking up here, this becomes negative 1 minus negative 1. That's 2. So there's how we're going to calculate it by hand. Looking down here at this one, again, in the boxy looking bracket thing, I put whatever gives me the derivative of 1 over x. I go back to my rule sheet and I find out that ln of x gives me a derivative of 1 over x. So the antiderivative of 1 over x is ln of x. I put my lower limit and my upper limit outside here. Allows me to take my antiderivative in one step and evaluate in the second step. So this is going to be ln of e minus ln of 1. ln of e is 1, ln of 1 is 0. So I've got 1 minus 0, aka just 1. And just to prove to you that I'm not absolutely crazy, I mean I'm crazy sometimes, but not in this particular case, I can do alpha window 4 integral from 1 to e of 1 over x dx gives me a value of 1. It feels so much better to do stuff without a calculator. But I think you guys know that I like doing stuff without a calculator better than I like using a calculator for it. Yeah. And finally, there's the assignment. This was fun. Let's do this again sometime.